you everyone for attending. I'm really excited to be giving this webinar. Um, and part of the reason why I'm excited to be giving this webinar is that I think everyone is familiar with the tools of surface science for analytical spectroscopy, and in particular, answering the big questions of what is at my surface and what is its chemical composition. These are questions that we have thought about, debated, and concerned ourselves with in surface science for a very long time. But the tools that we use to answer those questions can also be very easily adapted to answer a completely different set of questions, which is how does my surface behave chemically or electronically? And that's what we're going to be talking about today. Is in particular, we're going to be talking about 3 of those techniques that can be adapted from the traditional XPS, OJ, SIMS types experiments, and that we offer as part of our instrumentation for multi-purpose instruments for XPS. And the techniques that we're going to be talking about today are low energy inverse photoemission, UPS, and REAL, the reflection electron energy loss spectroscopy. As Sarah mentioned, we are going to split this up into 2 webinars, so not everything that was discussed in the original abstract is going to be in this webinar. And the reason for that is since I've been working with PHI and interacting with customers, what we've realized is that there's still a lot of confusion or questions surrounding some of the basic fundamentals of these techniques. And so the reason for splitting this up into 2 webinars is to make sure that we can bring everyone onto the same page and hopefully reduce some of that confusion and make these techniques, which are different from traditional XPS, seem less confusing or less daunting, and help people realize that these experiments or these techniques really can help them answer important questions about their science and their materials that they're looking at. So with that, let's go ahead and get started. All right, so we're going to split this up quickly into 3 sections. The first section is going to be some motivation and terminology, sort of why are we doing this, who's interested in this information, and making sure that we all have the same language that we're using. So surface science inherently is a multidisciplinary field. We have chemists and physicists, material scientists, engineers, biologists, people from all different realms of the physical sciences. And when we start talking about how electrons behave at these at surfaces or in materials, sometimes we come to it with field-specific language. And when I say band gap or electron affinity, I might be meaning something very slightly different than someone in a different field might be meaning by that. And I want to make sure that we're all on the same page so that we know exactly what these experiments are measuring and we can reduce some of that confusion. Then we're going to talk about the actual specifics of the techniques, how they work, how they get information out, and the exact information content that we get out. And then we're going to end by sort of comparing them and some of the key details of them. For the majority of data collection and best practices for making sure you get the highest quality data and data analysis are going to be pushed into the second part of the webinar so that we can launch into it and talk about it in a little bit more detail. Okay, so who is interested in this information that you can get from inverse photoemission, UPS, and REALs? Well, the first is people that are doing fundamental science. So I wrote, academics, but it could be the company and looking for fundamental science as well. And typically, these individuals are sort of pushing the bounds of knowledge that we have about materials. This could be either through synthesizing new types of materials, new classes of materials, or developing new techniques to explore them. So maybe they're pushing things into the attosecond realm for looking at electron dynamics or imaging or other advanced techniques. And that's not quite the target audience for this talk. Very grateful to those people, and I've been one myself. But what we're interested in right now is really we're going to be addressing this webinar to people that make stuff, whether it's electronics or photovoltaics, organic molecules, semiconductors, catalysts, because at the end of the day, most people aren't interested in just making a material. They're interested in making something that helps someone else solve a problem or serve a function. And the behavior of molecules and materials at interfaces is governed by their electronics, their electronic behavior. That's what governs chemistry. It governs electron transport. It governs almost all of the things that matter when you talk about materials and how things behave at surfaces. And for almost any purpose that you can imagine, understanding what the electrons are doing is a fundamental and key critical piece of information for how these materials will behave. And before we go any further, I just want to mention one little thing here, which is that there are many techniques for measuring the electronic states of a material that are sort of chemically and electronically active. So these are the electronic states that are near the Fermi level. Of all of the techniques that have been developed for this, UPS and inverse photoemission, including light, really are the gold standards for measuring those electronic state, which then govern the electronics, chemistry, and optical behaviors. And the reason why these are the gold standard techniques is that they're extremely pure techniques. The interpretation between the amount of interpretation required to go from what you see spectroscopically and what that is telling you about the electronic states is very small because it's a direct probe of the electrons in the system. And so these really directly probe this rather than indirectly probe it, which is why they're considered such a gold standard. What type of information are we talking about? Here's where we're going to start defining our terms. When we start talking about electrons at a surface, we have to talk about the electronic states that are there. We have our valence band. We're going to start from the bottom and work our way up here. So if we look down here, we have our valence band. At the top of the valence band, we have our valence band maximum. Now electronic states in the valence band are all filled with electrons. We then have our Fermi level. And if you don't remember, the Fermi level is just the energy at which below that energy, electronic states are filled. And above that energy, electronic states are unoccupied. They are empty states that you can put an electron into. So above that, we have our conduction band minimum, which is the bottom of our conduction band. We then have our actual conduction band where we can put additional electrons. And then above that, we have our vacuum energy. And this is probably the most confusing term in all of surface science. So the definition of the vacuum energy is the energy of an electron outside the surface of a material with zero kinetic energy. Now, to start with, that's obviously sort of a fictitious, idealistic level. Electrons never just go somewhere, sit, don't move, and remain there for all time to have a well-defined energy. But that is the definition of the vacuum level. You can tell that by definition, it's the electron outside the surface of the material. It is surface specific. If I have the same material, but I expose a different surface of it. So for example, maybe I have a metal and I have a different surface plane that I expose. So the 100 versus the 111 surface. These will have different vacuum levels because the vacuum level is a product of the surface dipoles of the electrostatics of the surface. So the vacuum level is not a global vacuum level. It is material and surface specific, which I think probably causes more confusion than anything else, any other term in all of surface science. The rest of the terms that we're going to talk about are terms that define the energy difference between energy levels, right? Because we can never actually measure an individual energy level. What has physical meaning is the energy difference between energy levels. So the first one that we're going to talk about is the work function. So the work function is the energy difference between the Fermi level and the vacuum level. If you're a semiconductor, that doesn't have a semiconductor insulator that doesn't have a ton of meaning because the Fermi level is falling somewhere inside the gap of your material. So there's no electrons at the Fermi level. If you're a metal, then the Fermi level crosses one of your filled bands. And so the work function also turns out to be the ionization energy. And the ionization energy, which we'll also hear referred to as the ionization potential, is just the energy required to move an electron from the system. Right? So this is just how much energy it takes to remove an electron from the top of my valence band and move it to the vacuum level. Next, we have the electron affinity, which is the energy released when an electron gets added to the system. So if an electron comes in here at the vacuum level, it can release energy and come down to the conduction band minimum, or the LUMO, and that energy releases the electron affinity. And then finally, we have the electronic gap, which is the energy difference between the valence band maximum and the conduction band maximum, or the conduction band minimum, excuse me. Or you can think of it as the HOMO-LUMO gap. Now, importantly, this is the electronic energy gap. It is actually not related to optical absorption, and we'll talk about that a little bit later. But this is the electron energy gap, the difference between the conduction band minimum and the valence band maximum. Okay. Now, for some of the audience, that's going to seem very intuitive. For the rest of the audience, it may have been a while since you took solid-state physics, or it just may seem a little rusty. And so I want to talk about the techniques that we're going to describe in a more intuitive manner. And so we're going to present, instead of talking about it from the sort of solid-state physics energy level picture, we're going to break it down into sort of a molecular picture, right? Because I think everybody who's doing surface science can recall back to their general chemistry and molecular orbital theory. So molecular orbital theory, we're going to bring together two atoms. They have electrons in their atomic orbitals. The orbitals mix together to create bonding and anti-bonding orbitals, and the electrons get shared in between them. So here we have two hydrogen atoms coming together to form molecular hydrogen. And when they do, they put electrons in their HOMO level, which is going to be the molecular equivalent of the valence band. And they have no electrons in their LUMO level, which is a molecular equivalent of the conduction band. And we're going to talk about how the techniques behave by looking at this molecular system so that we can get an intuitive understanding of what they're doing. Okay, so we're going to start from this diagram. We have electrons in our bonding orbital down here. And now what we're going to do, we're going to talk about optical absorption. In optical absorption, remember, I can absorb a photon if it has the energy that matches this bottom orbit, the energy difference between your HOMO and LUMO. And that will put an electron from down here up to here. And this is the optical gap. This is the energy required to promote an electron from the ground state to the lowest excited state. And that's the optical gap. Next, we're going to add an electron because this is what we do in inverse photoemission. In inverse photoemission, we're going to add an electron and we're going to look for photons that come out. But importantly, we're just going to add this electron and it's going to tell us information about what is the energy of this LUMO, or this excited electronic energy level. Now, you can imagine that this has an extra electron in it. This is at a different actual energy than this, right? Because the added electron-electron repulsion. And so this electron affinity is the energy required to add that electron is the electron affinity. And then finally, we can do the opposite, right? We can do our UPS equivalent, which is to have a photon come in, remove an electron, and ionize it to make a cation. And this will give us the ionization potential, the ionization energy. This is removing an electron, and we get left in this final state. And we do this to probe information about what the energy of the HOMO was. I mean, the energy gap, the electronic energy gap is going to end up being the energy difference between this state, which is the anion, and this state, which is the cation. Because the the electron gap, right, is the energy to put an electron into the conduction band, the energy of the conduction of the valence band, we're going to put an electron in there. It's more akin to electron transfer than it is to optical absorption. And so we're interested in the energy difference between the anion and the cation rather than sort of the neutral excitations of the species of the system. And so, great, but what is reals? Well, reals is a scattering process. We're going to have an electron that comes in with a well-defined kinetic energy. It's going to excite an electron from the HOMO into the LUMO. And as it does so, it's going to give up some of its energy to do that. And so when the electron leaves, by conservation of energy, it has to have less energy than when it started. And that energy loss is what we're measuring in the reals experiment. And that energy loss is telling us about the energy difference, the energy required to create this system, this first electronically excited state of the system. And you'll notice that this is the exact same final state that we got when we talked about optical absorption. And so reals is actually giving us a similar spectrum to the optical absorption spectrum. Okay. So why do we care about those? Well, the ionization potential and the electron affinity are the key parameters that you need to understand how energy levels align between different materials. So you need to know where the conduction band and the valence band are situated with respect to the Fermi level and the vacuum level in order to know when you put two materials together, how are their energy levels going to line up? And that is a key component to all solid-solid interfaces. So semiconductors, catalysts, batteries, anything that involves charge transfer, molecular solid-state sensors, all of that. And to get that, the techniques that you want to use are UPS and inverse photoemission or LIPes. The optical spectrum, or what you would get from reals, which if you're coming at it from a physics background is really the imaginary part of the dielectric function, or the stopping power of electron stopping power of the material, is going to give you information about a material's ability to interact with light. So extremely important parameter for photovoltaics, photonics, optical sensors, but it doesn't tell you anything about where those energy bands are situated. It just tells you the excitation energy to excite an electron in the system. And these are clearly not the same information. And from the example and from the explanation that I'm given, I don't think they sound like the same information to anyone. And yet, when you look in the literature and you look in the community at large, you will find many examples where people assume that these two are giving you the same, these two sets of techniques are giving you the same information. That the band gap that you would get from UPS and LIPes is going to be the same as you would get from reals or from optical spectroscopy. And they're not. They're complementary information, but they are fundamentally different. So why does this confusion seem to exist? Well, I think the real reason for that is actually historical. Inverse photoemission as a technique has only been around since the 1980s. But people have been studying excited states of systems for long before that, as well as once it was invented, inverse photon emission was extremely difficult, and it damaged almost any material that wasn't extremely robust. It would damage and destroy. And so it was a difficult technique to do. It wasn't done very often. People wanted that information. And if you're talking about metals, right, which is where a lot of surface science got its start and has been done, in a metal, the electron affinity, the ionization potential, and the work function, they're all the same nominal value. In a metal, you have infinite screening, and so the optical spectrum ends up being the same as the energy difference between the conduction and valence band. Well, there's no band gap, but it ends up being the same. And in low band gap semiconductors or highly doped semiconductors, there's also a lot of electron screening, and so the physical information between the two experiments ends up being very, very similar. And so this led to the idea that you could use UPS to measure the ionization potential, and then reals or UV vis to get the electron affinity, or at least where the conduction level, the conduction band minimum is. And it's formally incorrect, but it works for some systems, and people apply it outside the realm of where it actually does work. And this fails. Where this stops working completely is in molecular systems, and in systems that show strong optical features. So systems with large exciton binding energies or strong excitonics, or in general, low dielectric constants also tend to show very different data between reals and inverse photon emission and UPS. So it's formally incorrect, but most people know that, though not everyone does, and that's sort of the difference between the two. I just wanted to clear that up at the start of this talk. We're going to start talking about the individual techniques. And the first technique that we're going to talk about is the one that I think gives the most confusion because it's the least like other surface science techniques, and this is low energy inverse photon emission spectroscopy. So this is a technique where we're going to shoot electrons at the sample and look at the photons that come out to get information on what is the energy level of the conduction band minimum. And we're going to talk about this technique in two ways. We're going to start by looking at just what the electrons are doing, and then we'll talk about what the photons are doing. And to help with this, I have a little video here that I made. See if we can get it to play. Oh, here we go. We have electrons coming out, and they're low energy, about 5 electron volts or less, and that's low enough to avoid sample damage. Those electrons flow into the sample, and that's the low energy electron transmission. And then we're going to apply a bias to that. It's going to cause the electrons to slow down as they hit the sample and eventually get repelled. So let me go over that again real quick. We have our electrons coming out with a fixed kinetic energy. They come into the sample. That creates a current, which we call the LEET, or the low energy electron transmission current. So it's the current that just gets transmitted through the sample. We measure that with an ammeter, and we apply a negative voltage to the sample that slows the electrons down. We'll watch this one more time so we can all see it again. So the electrons come down, go into the sample, we measure that current, and then we start to slow it down. And eventually, we reach this point right here where the electrons turn around, and they actually do go back to the electron gun. This video is accurate. And we're going to call this the LEET inflection point, or the inflection voltage. And we'll notice that when the electrons turn around, that means they're getting to just outside the surface of the sample. Turning around, they have to have zero kinetic energy at some point when they turn around. That is the vacuum level. So that LEET inflection point is telling us what the vacuum level, what voltage we need to apply to get electrons to the vacuum level for this material. Okay, so that's the electrons. Now let's look at what happens to the photons. So here we have our electron beam coming down, and when they come into the sample here, so here's the conduction band of the sample and the valence band, the electrons get to the conduction band of the sample, they can relax and emit a photon when they do so. Now, this electron can relax down to here, or here, or here, or here. And so it can emit many different wavelengths of light. We're going to use a filter to select, bandpass filter, to just select one. We're just going to look at one wavelength. Now we're going to apply our negative bias. The energy slows down, and eventually we reach that point where the electron is still making it into the sample, and that photon energy just makes it to, sorry, let me this off here. I'm going to just put it right there. There we go. That light's onset voltage, right? So that photon energy comes right down here to the bottom of the conduction band. And when we lower the electron's energy outside the surface anymore, it can't give off a photon of the wavelength that we're looking at, because it would have to come down to an unoccupied state, which is in the band gap. There's no electronic state down here for it to go to. And so it cannot release a photon of this energy. And so we see that our photon intensity goes away. And that is the light's onset voltage. Now, that tells us where the bottom of the conduction band is. We know the bottom of the conduction band. We know the voltage that gets us to the vacuum level, right? That's our lead inflection voltage. Well, that's all the information we need to calculate the electron affinity. And so the electron affinity is just the photon energy that we're looking at minus the quantity of the light's onset voltage minus the lead inflection point. And that's a lead experiment, a Light's experiment. Now, in order to make this work, the electron affinity has to be smaller than the energy of the photon that we're looking at. And that is one key consideration when setting up your Light's experiment. That has to happen. The other key consideration you'll notice is that we are measuring the current that flows through the sample, and that is an important part of this experiment. And so if electrons are not able to flow through your sample, if your sample is highly insulating and your surface starts charging, then this lead inflection point won't make any sense. Your sample will charge and your curve won't look like this. It will just start to repel more and more electrons, and you will not get the correct result. So a Light's experiment requires a bandpass filter with photon energy higher than the electron affinity of the sample, and the sample has to be reasonably conductive. Okay. Now, what is the big deal about light versus conventional inverse photoemission? The big deal is that light does not damage most materials. Conventional inverse photoemission uses a an electron Geiger detector to detect the UV photons, and it's limited to detecting photons that are around 10 eV in energy, which means it has to use electrons that are at least 15 electron volts in energy in order to do the experiment. That's enough energy that the electrons can interact with most molecules and break bonds. Whereas for light, because we detect photons at a lower energy, the electrons can be a lower energy, and below 5 eV, most materials do not get damaged by electrons. And this opens up massive territory that's been unexplored by inverse photoemission and makes a whole range of materials now accessible for this sort of direct measurement of the conduction band. Okay, so here's what this looks like. Here is just an example of this. This is conventional inverse photoemission, where they have their electron beam. And you can see that after 10 minutes, the intensity of the conduction band starts to decrease because we're damaging the sample. Same experiment, same type of material, but we do it with lights, keeping our electrons under 5 electron volts. And you can run this experiment for hours without any evidence of sample damage. Okay, so that's the big deal with LIPEs. So we're going to run through a very quick example, and this is going to be pretty quick. But this is an example that from data that we did with a customer at Stanford with Juliet Jamgard and Tyler Quill. This is a semiconductor polymer that's used for organic photovoltaics and organic semiconductors. It's called IDTBT C16. And it's used as a whole transport layer and optical absorption material. Here's a photograph of what the sample looked like. And just some experimental details. This experiment was done using an electron source that had electrons at 8 eV, and you used a 260 nanometer bandpass filter, so 4.7 eV bandpass filter. This sample was made specifically to do LIPEs and UPS. So it's a semiconducting polymer, which would be too resistive to look at in the bulk, but we made a thin film of it, roughly 20 nanometers, and spin coated that onto an ITO substrate. So ITO is conductive, and that provided enough conductivity to be able to do these measurements. The sample bias was scanned here from -3 volts to -9 volts. You'll notice that 8 minus 3 is 5. And so that means that the landing energy of the electron the landing energy of the electrons was never greater than 5 eV. And so it didn't damage the system. It didn't damage the polymer. And we took multiple scans of this, verifying that there is no sample damage or charging that happened, and also to increase the signal to noise. And this is what the data looks like. This is collected simultaneously. We have our lead current, which is the current flowing through the sample as we change the bias. We have current, none. And then we have our photons, and we're measuring these in our photon detector. And you can see we have photons that turn on right here. Just very quickly, we need to find the inflection point for this. The way that we do that is that we differentiate it. Right, so here's the multiple spectra that I told you about. We do it multiple times, we average them. We want to find the inflection point. You can just numerically differentiate that and look for the maximum. And that gives us our lead inflection point, which tells us about the vacuum level. And you'll notice that this isn't at 8 volts exactly, -8 volts. And that's because there's a work function difference or contact potential difference between the electron gun and the surface of the organic semiconductor. And that's going to be typical. It usually won't be, your lead inflection won't be exactly at -8 volts, which is why we need to measure it. And then we looked at the onset of the light signal. We use the pretty familiar tangent slope methods, right? So we just see where does, near the end here, where does the slope of this tangent line intersect the background? To find that onset voltage, we plug that into our formula and we get an electron affinity level 3.25 electron volts. And this exactly matches what we expected from other techniques and other measurements on similar samples. So that's it. It's a pretty straightforward experiment once you understand how it works. All right, so that's probably the most confusing of the techniques. So we're going to talk about reals, UPS and reals next. We're going to do that a little bit more quickly. So with UPS, it's light in and valence band electrons out. This is much more akin to traditional XPS measurements that you might be more familiar with, which is why we're not going to spend quite as much time on how the technique works. But instead, we're going to focus on what are the differences between XPS and UPS. So, right, this energy diagram where we have light in, photoelectron out, and we add some kinetic energy, and that kinetic energy tells us what the binding energy of it was. This diagram looks the exact same for UPS and XPS. But there are some key differences. Obviously, the photon energy is different. So in XPS, we're talking about X-rays. UPS, we're looking at UV light. The energy resolution is different. So XPS has an energy resolution typically on the order of 0.5 eV, and that's what I mean by the energy resolution here is the full width half max of a feature, not your ability to locate, sort of a charging shift, which is obviously much higher, but the ability to separate different features from each other. the orbitals or the features that we're looking at are, sorry, in an UPS, it's much smaller, about 50 millielectron volts. XPS is looking at orbitals that are localized to individual atoms and specific to an individual atom, whereas UPS is looking at frontier electron orbitals, molecular orbitals that are much more delocalized. XPS has a larger information depth, so typically roughly 10 nanometers, whereas UPS has a much smaller information depth, roughly around 1 nanometer or so, so just a couple of layers at the surface. And that's because the inelastic mean-free path of these lower energy electrons is much smaller. The energy dependence. So if I look at the XPS spectrum of, let's say, an aluminum K-alpha XPS at 1400 eV versus a magnesium one at 1200, the spectrum are going to look very similar. So it doesn't have much of an energy dependence to the spectrum. In UPS, that is not true. If you look at a UPS spectrum that's taken at with a helium-1 source at 21 eV versus a krypton or a neon source down at 16 or 11 eV, they look different. They're not probing just the density of states. They're also probing the transition dipole moment, and that has a strong energy dependence. So just something to be aware of, that when you look at UPS spectra that are taken with different energies, they will look different. And then finally, XPS spectra, you can have contamination and you can see it, but it will not obscure the spectrum of what is the composition of the material underneath. Whereas with UPS, because of the delocalized bonding, because it's only probing the surface, when you have contamination in your UPS spectrum, you will wash out the features that you're actually interested in. You won't be able to see that. So UPS and LIPES as well are just much more sensitive to what's going on at the surface and any contamination. By far, the most common system for taking lab-based UPS measurements are using a helium-1 gas discharge lamp, which has a photon energy of 21.2 eV, followed by helium-2, which is just the 1s to 2s transition for the helium plus cation. But you will also see some experiments that are doing UPS with neon and krypton, argon as well. And in fact, most lamps that can do UPS with helium can also do other noble gases. So just something to keep in mind. All right, this is what a UPS spectrum looks like. So this is a UPS spectrum of silver. I just want to point out a couple things. In this region, sort of near the valence band, you will often have a variety of features from the conduction or from the valence band. These are difficult to predict unless you do electronic structure calculations. Right? They're not specific to an individual atom, but instead to how the chemical environment that the electrons are experiencing. They're delocalized, and they're very sensitive to chemical bonding. So you can't predict these without doing, DFT or some other electronic structure calculation, but they are very specific to every individual material. And so you can use these features as fingerprints for, is a species present at the surface? And because it's so surface sensitive, it's a much more sensitive measurement even than sort of XPS, right? So there's a lot of literature out there. People have done this with polymers and others, some semiconductors, ALD, to look for particular bonds at the surface. But in this talk, we're really focused on electronic structure measurement. So, how do you measure the electron affinity, ionization potential, and work function? So this is a metal, silver, so the ionization potential and the work function are the same. And the Fermi level is crossing our UPS spectrum at zero binding energy by definition, right? So it is conducting and it's in contact with our chamber, so they share a Fermi level. So we can measure that quite easily right here at zero binding energy. And then we would expect that when you have, this is taken with the helium lamp, so it has a photon energy of 22 electron volts, or 21 electron volts, excuse me. When the energy of your orbital, the binding energy of that orbital, plus the work function of your material equals the photon energy, then you will have no signal below that. So you'd have a sharp cutoff at some point at high binding energy. But when we look in our spectrum, we don't see that. And the reason we don't see that is that would be for electrons just making it to the vacuum level, so they have no kinetic energy, so they don't make it to the detector. And in order to see them, we just need to apply a small negative bias to the sample, and that bias is between the sample and the detector itself. So it's not enough electric field to really alter the position or doping or behavior of these energy levels. It just helps to accelerate them so that these electrons that make it here near zero kinetic energy can make it to the detector and we can spot them. So if we take silver and now we apply a bias to it, we can very easily see this cutoff. Here we have in red the spectrum that I just showed you of the original UPS spectrum of silver. And in blue, we have our UPS spectrum at minus 10 volts. I apologize for that confusion. We have our Fermi level up here crossing at minus 10 volts. And then we can easily look at our conduction. We can look at our secondary electron cutoff, or our cutoff energy here. And we can't determine any difference between electrons that get there because they were directly photoemitted, or electrons that were photoemitted with some kinetic energy and scattered at the surface down to zero kinetic energy. Doesn't matter which process happened, it's giving us the same information. We measure where that crosses the background, we subtract that from the photon energy, and we get our work function or ionization potential. So we can get that ionization potential just by subtracting the spread, the spread between the cutoff and the onset of our UPS spectrum. And that's all we need to do to get the ionization potential. Now, one thing I wanted to point out, right? I mentioned earlier how UPS was so surface specific. That means that it's sensitive to contamination. One of the most common things that can be a problem in acquiring UPS data is sample cleanliness. So here I have a gold foil, and if I look here at this cutoff region, you'll notice that there's this long tail out here that's ugly and broad. And even though the sample was gold foil was brought in and sputter cleaned, it wasn't sputter cleaned sufficiently to remove all of the contamination that was present at the surface. And you'll see that this results in these sort of shoulders that appear in the cutoff region, and it pushes even this part that looks like it might be the gold cutoff is also too high, which means you would measure a work function value that is too low. Okay, and so it is extremely important when you do UPS experiments that your surface is clean and as free of contamination as possible. All right, so real quick, we just want to do a semiconductor example so you can see the ionization potential. So this is molybdenum ditelluride. This is an indirect bandgap, low bandgap semiconductor. I'm not going to go through do the exact same thing that you would do for the metal, except now, instead of looking at our Fermi level crossing at zero binding energy, we're looking at a valence band maximum or HOMO, and we look for the onset of that, which occurs at some value less than the Fermi level. And again, we look at the secondary electron cutoff. Because we're looking at the secondary electron cutoff, we again have to apply a bias in order to measure that, but we can then get our ionization potential. Easy peasy, 1, 2, 3C. So that's a simple way that we can use UPS to measure the ionization potential. And again, it's very straightforward once you understand how the experiment works. Okay. So we now have a way of measuring the ionization potential, the electron affinity, and the work function, right, which is just where the Fermi level is relative to the vacuum level. So we can start putting these things together. But when we do that, I just want to make a point here real quick that there is a big difference between LIPS and UPS. The magnitude of the signal in UPS is much higher than the signal for inverse photo emission. And there is unfortunate physical limitations to that. And the reason for that is that the cross section for having an inverse photo emission process versus photo emission is approximately the wavelength of the electron versus the wavelength of the photon divided by the wavelength of the photon squared, that ratio of cross sections, which means that UPS, or the photo emission process, is approximately 100,000 times more likely than the inverse. It's just a lower probability that when you shoot an electron in, you'll get a photon out than shooting a photon in and getting an electron out. Okay. And so obviously that means that we're always looking for ways to increase the signal of light so that we can acquire that data with high signal to noise faster. And you can do that by making sure your sample is clean, well prepped, you have longer acquisition time, or you can increase the sample current. But there's a caveat. Even though LIPS is designed to minimize sample damage, you can still have a very low rate of sample damage for some systems with zero kinetic energy electrons because of the energy that gets released when the electron goes from the vacuum level to the conduction band minimum, right? It needs to release that energy. And so that can still cause damage in some systems. The rate is low, but the more current we have, the more likely that is to happen. And so the temptation may be to increase your current to get more signal, to get more photons out. But if you do that, you need to be very careful that you're not damaging your sample while you do that. So just a note of caution. Okay, but that said, we now have our UPS, our LIPS. We can measure the valence band with UPS, the conduction band with LIPS. Well, now we can put them together, right? We have a way of measuring each of these energies. Now we can relate that to the spectra. And importantly, what this gives us, because we're able to reference these to the same energy level, whether it's the Fermi level or the vacuum level, depending on what you're interested in, it tells us where these things fall. And so we can start relating one material to another material and look at what is the electron injection barrier, the hole injection barrier, or the hole collection barrier, right? So we can talk about how do electrons transfer between materials by this sort of unified band structure that we can directly access experimentally. And so here's an example from the literature. This is from Hiroyuki Yoshida's lab in Japan, who is the inventor of LIPS. And so I wanted to give him some props and credit for developing this technique. And what he was looking at was organic molecules that were whole electron transport layers in a perovskite-based solar cell. So this is ammonia methyl lead triiodide perovskite. And what he did was he wanted to look at what is that charge injection barrier and what does that band bending look like. And so he took a layer of the perovskite and then deposited fullerene layers on top of that and looked at how the band structure changed relative to both the vacuum level and the Fermi level in that system. And so they could directly get the band bending and charge transfer barriers. So it's a really powerful combination of techniques that do something that you can't do through any other technique. All right, and then finally, we're going to do this pretty quickly for the reals. But reals, reflection electron energy loss spectroscopy, is electrons coming into the sample and then being scattered away. Okay, so experimentally, this is what it looks like. Let's replay that animation again. An electron's coming in, gets scattered by the sample, and then excites an electron into the excited state. That's an inelastic collision, and that slows the electron down. Now, here we have a real spectrum of hafnium dioxide, where we measure the kinetic energy of the electrons. This is being done in an XPS instrument. So we have an electron energy analyzer. We can use the exact same energy analyzer. You'll see that the vast majority of electrons are just scattered elastically, right? No change in energy. But if we zoom in on this region, we can see this is the tail end of that elastic peak. We have this region down here where there is no signal. And that is because there are no electronic states of that energy in hafnium dioxide for the electron to excite as it goes past. We can measure that onset, and we measure 984.3 eV. This was a 1 keV beam coming in, so our loss is 5.7 electron volts, and that matches the band gap of hafnium dioxide. Now, you may notice that I said matches the band gap. The reason why it matches the band gap for hafnium dioxide, I didn't call it the optical gap, is because hafnium oxide is so insulating that it's hard to actually measure a band gap in hafnium dioxide. And so the optical gap is effectively what we refer to as the gap for hafnium oxide. If you go in the literature, you will see that that's what people refer to as the gap for hafnium dioxide. It is formally the optical gap. But this works really well. And you can do this with hafnium dioxide. Silicon dioxide is a very famous example. Silicon dioxide has a gap of 9 eV. Excuse me, 9 eV. And that's something that you can't easily do with LIPEs because we're looking at UV photons. And remember, the electron affinity needs to be smaller than the photon energy that you're looking at. And in LIPEs, because you have your detection outside of vacuum, you can't really look at anything with a photon below where water in the atmosphere starts absorbing, which is at 193 nanometers or 7.1 eV, 6.9 eV, I forget what. But for large gap materials, or really strong insulators, REALS is a powerful technique that can analyze systems that UPS and LIPEs struggle with. One other thing that I want to point out along those lines, right? This does not transfer an electron to the sample. It is formally neutral. And because of that, it is much easier to do REALS on insulating surfaces. We don't need to measure the current transmitted through the sample. And then finally, REALS can do one additional thing that LIPEs and UPS cannot do, which is REALS can detect the presence of hydrogen. So these electrons that we detect in REALS are being backscattered, which means that they're coming extremely close to the nucleus. They're interacting strongly with the Coulombic potential. But when they do so, they're not just transferring, they're not just doing an energy transfer, they also have a momentum change, right? The electron is changing direction. And that momentum has to get transferred to the nucleus that it's scattering off of. Now, for most atoms, you transfer that small amount of momentum. The nucleus is so heavy. Yes, there's a very teeny tiny energy shift, but you don't really see it. But hydrogen is so light that energy, so you transfer that momentum, the hydrogen picks it up as p squared over 2m kinetic energy. The electron has to give up that energy to do that. And so that means that the electron actually loses energy in that elastic collision because it's transferring it to the hydrogen through momentum transfer. And so you get a recoil energy. And that recoil energy, for depends on, the mass of the electron. This is the mass of the nucleus, your scattering angle, the sine of the scattering half angle squared times the kinetic energy of the incoming beam. So you can detect hydrogen by looking at there will be an additional feature in your real spectrum, and that feature will be energy dependent. And if you go to a higher electron beam energy, you get a larger recoil energy or a larger energy loss for your hydrogen peak, which allows you to identify it unambiguously as coming from a recoil feature as opposed to anything else. It's beyond sort of the scope of this particular talk, but I just wanted to mention it because it's so powerful, and you get it for free when you do reals. All right, so last thing that I want to talk about is just this sort of comparison slide to go over the three separate techniques, right? So remember, LIPES is detecting unoccupied electronic states, UPS is detecting the occupied ones, and REALS is detecting the electronic excitations. They have different energy resolutions, with UPS being the highest, and then LIPES and REALS being roughly comparable. LIPES and UPS give you the energy band alignment, the energy band alignment of your bands and the actual bands that you're looking at, which allows for comparison between materials and electron transfer. REALS does not. LIPES and UPS have extremely high surface sensitivity. REALS has high surface sensitivity, more comparable to XPS or OJ spectroscopy. And there is a differentiation of signals that come from the surface versus the bulk. That's beyond the scope of this talk, but you can see through carbon contamination in REALS in a way that you simply cannot with UPS and LIPES. For LIPES and UPS, you absolutely need conductive samples. Especially if you're absolutely required for LIPES. For UPS, if you want the work function or the ionization potential, you absolutely need a conductive sample. And for REALS, you do not. Can you use the neutralizers to help you out? Well, no, you can't, unfortunately, for LIPES. You're looking at low energy electrons, so you can't shoot additional low energy electrons at it without perturbing your experiment. For UPS, you actually can use the neutralizers if you're interested in that fingerprint region. You can use the neutralizers. People have done this looking at polymers, but you cannot use them if you're interested in the work function or ionization potential. And for REALS, you generally don't need to. The possibility, of surface chemical damage with LIPES, it's extremely light. For UPS, I would say it's light to medium. It depends on how long you're exposing your sample to the UV photons. Those can do damage. You just want to be aware of that. And with REALS, you have a high probability of chemical damage to your sample. That's very easy. Sensitive to vacuum contamination, high, low. And then finally, last size, I wanted to give you sort of the minimum sample size on sort of PHI Genesis, or this would also work for a VersaProbe. So if you have a physical electronics instrument, we recommend for LIPES a minimum size of 6 by 6 millimeters, preferably 1 centimeter. And we would say the same thing for UPS. A larger sample helps with uniformity. The actual beam size of the measurement for LIPES is roughly 2 millimeters. For UPS, it's about 1.5. But you want a larger area so that you have uniform electrostatics in the area that you're measuring. And then for REALS, you can actually do it with a much smaller beam. If you're doing this with our OJ gun, you can do it with just a few microns. If you're doing it with the sort of the standalone dedicated REALS gun, then you would need a comparable size to the UPS and LIPES. You would need several millimeters in order to do it. But hopefully, that's sort of a comparison between the techniques. Hopefully, this talk is explained a little bit more about the background of these techniques how they work and given you an idea of whether or not they might be appropriate for the systems that you are interested in studying. They are powerful techniques for measuring how materials behave electronically, chemically. UPS and LIPes give you a unique piece of information, which is the energy alignment of different bands. And that information is complementary to the excitation energy that you get from reals. Special care needs to be taken when you're doing a UPS and LIPes experiment that you have enough conductivity that the current going through your sample has a way to pass through without charging your sample and giving you erroneous results. And that means that you need to design your experiment towards measuring the electronic structure of the material rather than sort of taking an experiment where you do XPS and just saying, oh, hey, maybe we can do LIPes or UPS on this. If you want to measure the electronic properties of these materials, you want to start from that and then do XPS on them rather than the other way around, because they require a little bit additional care and concern. I'd like to thank Juliet Jamgard and Tyler Quill from Stanford for letting us use their sample and present that data. Sarah Zachary and Jenny Mann, David Valley, Katerina Archishkova for all of the help in the lab, the rest of the PHI lab as well, and then everyone here for your attention and letting me talk to you about this. Thank you so much.